Hello everyone, welcome back. So in today's video, we are going to cover two problems which are based on pretty much the same concept. So we are going to be learning a neat trick when it comes to dealing with elastic cords. After this problem, we will take up a problem from Pathfinder. And before we begin guys, I have a small request. So make sure you share these videos with your friends guys. And if more people find these videos useful, I'll be making more of these videos. Okay, so with that, let's start with the first problem. So I translated this question out of Google Translate, so that's why the language is a bit weird. I'll explain the question properly, okay? So we have two rubber bands and then we have a washer of mass M that is held at point O on a horizontal surface. And they're connected to two weightless rubber bands threaded through smooth rings B and C fixed to this surface. The other ends of the rubber bands are fixed at point A and D. Okay, so this is the diagram that is given to us. So the washer or the mass M is present at this point O and then it's connected by two rubber bands, okay, which extend like these, and the other end of the rubber bands are fixed at point A and point D. Okay, the lengths are all given in the diagram and it's given that the natural length of the rubber band is equal to capital L. Okay, now the stiffness coefficient is of rubber band OBA is equal to K and that of OCD is equal to 3K. So basically the band on the left has a stiffness coefficient of K and the band on the right has a stiffness coefficient of 3K. Now the coefficient of friction of the washer on the surface is mu. So there is friction in this horizontal surface. Okay, acceleration of the gravity is given to be G and now the washer is released. Okay, now when it is released guys, obviously the string is going to be pulling on it and the bead O will be accelerating. So we have to find the maximum speed of the washer during its further motion. Okay, and then we have to determine the time tau at which the maximum speed is reached. Okay guys, so give this problem a good try for like 5 to 10 minutes and then check out the solution. Okay, so firstly the band on the right has a spring constant of 3K and the band on the left has a spring constant of K. Okay guys, so now let's analyze the forces acting on the bead M. It's given to us that both the bands have a natural length of capital L. So if you look at the band on the right, the part CD has a length of L, right? Which means the part OC of the rubber band is the extension. Similarly, the part BO is the extension on the left rubber band. So basically, if we analyze just the right rubber band, the force is going to be the stiffness constant 3K multiplied by the length OC, right? So basically the force is only dependent on this distance OC, and similarly the force on the left rubber band is only dependent on this length BO. So let's say I define my origin to be at this point C, okay? And let's say I draw a position vector. Okay guys, so now what I'm doing is I'm assuming this point C to be an origin and connecting it to the point O and calling this vector as CO vector. Okay, so the advantage of doing this is that the force applied on the mass M due to the right rubber band, this force F is just going to be 3K and it's opposite to CO vector. So I'm going to write it as minus CO vector. Okay, so again the magnitude is going to be 3K times this distance CO and the direction is opposite to CO vector. Okay, now similarly let's define BO vector for the other rubber band and the force is going to be K times minus BO vector, right? Because the spring constant of the left band is K. So let's call the net force as F vector. This will be just a vector sum of both of these forces, right? So it will be minus 3K times CO vector minus K times BO vector. Okay, so this is where the trick comes into picture. So I'm going to write CO vector as this vector plus this vector. Okay, so basically I'm expressing CO as a sum of two other vectors. So this particular vector, I'm going to call it as, let's say, A vector. Okay, so let's call this point as O dash. Alright, now F vector I can write as minus 3K. Now CO vector I'm going to write it as A vector plus O dash O vector. So BO vector I'm going to write it as, now this vector guys, it is nothing but minus of A, right? Because A vector was towards the left, so this vector will be minus of A and they have the same magnitude, right? So these two vectors are just anti-parallel to each other. BO vector is going to be minus A vector plus the same O dash O vector. So now let's take the similar terms common. So now let's take minus 4K outside. Okay, so now let's try to figure out what is this particular vector over here. So O dash O vector is basically this vector over here in the minus J cap direction, and we have to add half of A vector to it. Now this complete vector was A vector guys, so half of A vector would be this particular vector over here. So if I add both these vectors, I'll get this particular vector over here. So which is basically the vector originating from this point. Let's call this point as D. So basically this vector over here is vector DO. Okay, so let's draw a better picture. All right. So this is O dash O vector and this is A vector by 2. Their vector sum is this particular vector over here. Let's call this point as point D Now if I connect the vector D to our point O, this vector over here that we just figured out is nothing but vector DO. Instead of calling it DO, let's just call it as R vector. So this force just simplifies as 4K times R vector. And finally, this complicated looking expression, we now simplified it to this very easy expression. So now what this force expression basically means is that if the particle is at a distance of R from the point D, the force is going to be towards the point D and its magnitude is going to be 4K times R. And with this, the job is actually pretty easy. We don't have to care about anything else. All we have to do is observe point D and point O. Okay, so let's say this is point O and let's say this is point D. At any general time t, the distance between these 2 points is R. The mass is present over here and the force on the particle, it will be towards the point D and its magnitude is 4kr. This is what we determined. Okay, so the net band force is towards this point D, which means the particle will start moving in this direction OD, which means friction force will start opposing the particle once it starts to move, right? So the friction force on the particle will be towards the left initially, and its magnitude will obviously be kinetic, which is mu mg, right? So now let's write down the differential equation. So this was my vector r initially, right? Usually in the direction of r, we assume the acceleration as well. Acceleration of the particle is in the direction of the position vector itself. So we can say the net force acting on the particle, which is minus 4kr plus mu mg. So this is the net force acting towards the left. This would be equal to the mass times the acceleration of the particle. And acceleration of the particle, I can also write it as r double dot. So from here, what we get is mr double dot equals, now what I'm going to do is take minus 4k common, and this becomes r minus mu mg by 4k. Okay, so this differential equation is the exact same differential equation that we get for a simple harmonic motion. The only difference is that this is a shifted simple harmonic motion, right? Meaning the equilibrium position is not at r equal to 0 or d point. It is actually at r equals mu mg by 4k. So I'm going to write mu mg by 4k as some r naught for now. Okay, and I'm going to write r naught over here. So basically r equals r naught is the equilibrium position, and that will be somewhere over here. Okay, so let's mark the equilibrium position with green color, and it's at a distance of r naught from the point D. Okay, so now let's observe the motion of the mass m. So initially the spring force is greater than the kinetic friction force, so it will obviously accelerate, right? And the particle will keep accelerating till the equilibrium position, and once it crosses the equilibrium position, then friction force will dominate. So basically m mass will keep accelerating till the green point is reached. So basically the green point is nothing but the equilibrium position, and the point O, you can consider it as the extreme position, right? So basically we want to figure out the time it takes for the mass m to go from extreme position to mean position in an SHM. We can apply the results of SHM here, but that doesn't mean it will keep on oscillating, right? Because the friction force will keep killing the mechanical energy of the system, and after some time definitely the particle will come to rest. But as the differential equation is exactly the same as the SHM differential equation, we can use all the results of SHM for this time duration. Okay, if I want to figure out the time taken to go from extreme position to mean position in an SHM, then the result is pretty simple, right? So its total time period is 2 pi by omega. So I'll send to m to the other side. So basically this coefficient is what we define as omega squared. So the time period is going to be 2 pi square root of m by 4k, and the time taken to go from one extreme to to the mean position is 1/4 of the total time period. So basically we'll just divide this by 4. So the answer just becomes pi by 2 square root of m by 4k. So this is the answer to the second question. So yeah, that would be this particular value. Now the question is, what is the velocity? Now the velocity at the mean position, again we can use the standard result from SHM. So the mean position velocity is equal to a omega. Okay, so now we have to be extremely careful, guys. The amplitude of the SHM is defined as the distance between the equilibrium position and the extreme position. So this is my amplitude. Okay, so I know this distance is r naught, which is mu mg by 4k. So we have to figure out the initial distance of O from the point D, which we can figure out using Pythagoras theorem, right? So this distance was given to be L. This distance would be L by 2. So the initial value of r is square root of L square plus L square by 4, which is root 5 L by 2. So the amplitude is the distance OD minus this distance, which is R naught. This just becomes root 5 L by 2 minus R naught, and this multiplied by omega, which is square root of 4k by m. Okay, and once you substitute the values in, you'll get the velocity at the mean position as this particular value. So that was the analysis to this problem. So now let's try to solve the Pathfinder problem. Okay guys, so in this question we have 3 identical elastic cords and all of them have a force constant of K and they have 0 relaxed lengths, okay, which basically means the length of the string is the extension itself, okay, and they're connected to a particle of mass m and the other ends of the cord are connected to 3 equally spaced points A, B and C on a rigid ring that is placed on a frictionless tabletop. So guys, there is a slight problem with this particular line, okay, and that we'll discuss in a bit. So mass of the ring is given to be 2 times the mass of the particle. Now it's given that in equilibrium the system stays at rest with the particle at the center of the ring. So well, initially the particle is at the center of the ring and the elastic forces are at equal angles of 120 degree and all of them have the same magnitude. So net force is 0 and hence it will be in equilibrium. So now the ring is held and the particle is pulled horizontally to a point P that is at a distance of R0 from the center O of the ring, and both of them are set free simultaneously. Okay, so then we have to find the period of the oscillatory motion and then we have to figure out their location. And then in the second question, they told us to assume the initial location of the center of the ring as the origin. So initially where the ring was present, right? At that location, the center of the ring O is to be taken as our origin and the line OP as the x-axis. We have to express the particle's position and the center of the ring's position as a function of time. So basically both the ring and the particle will move. So we have to figure out both of their positions. Now guys, there's a slight problem in this question. So initially it's given that the ring is placed on a frictionless tabletop. I mean, definitely in this question, the gravity is not mentioned. So we'll ignore that. Even other than that, if I pull the ball by a distance of R0 and I release it, I'll explain this while we do the analysis, but let's say this was the table and this is the ring and this is the particle, okay? So the ring will be pulled up and the particle will be pulled down. So what happens is if there is a table over here, this particle will actually collide with the table and we don't have to include that under the analysis, okay? Basically the problem setter did not take that into account, so we have to ignore that, okay? So another way to frame this problem would be, let's assume this ring is in a gravity free space and then this particle was displaced by a distance of R0, okay? So we are going to be using this assumption while we solve the problem. Okay guys, so again we'll use the same trick that we used in the last question. So let's talk about this string BP first, okay? So this BP vector, I can clearly write this as BO vector, right? Plus OP vector. Now guys, this OP vector is perpendicular to the ring. So if this is the plane of the ring, this is OP vector, okay? So we can say BP vector is equal to BO vector plus OP vector. And similarly, we can say AP vector equals AO vector plus OP vector. Okay, and similarly CP vector equals CO vector plus OP vector. So again, the reason for doing this is still the same. It is to write the net force on this mass M. So the net force on this mass M is going to be minus K times BP vector minus K times AP vector minus K times CP vector. So I'm going to take minus K common and inside there will be sum of BP, AP and CP. So now if you add all these 3 vectors, on the right side there will be BO plus AO plus CO. Now BO, AO and CO are in the plane of the ring, guys. So if you observe these vectors, these are just, so this is going to be BO vector, this is going to be CO vector and this is going to be AO vector. And they all have equal magnitudes and they make an angle of 120 degrees with each other, which means their resultant is going to be 0. So these 3 vectors added together will give us 0 resultant. So basically on the right hand side, we'll just end up with 3 times OP vector. So let's just name OP vector as R vector, okay? So this just becomes 3 times R vector. So finally, this is not M, this is F. So finally the net force on the mass small m comes out to be minus 3K times R vector. So basically we can treat this entire system like this. So from the center of the ring, if let's say this distance is R and let's say this is where the mass M is placed, the net force on the mass M is going to be 3kr towards the center of the ring. So this is basically the whole idea. Okay, so this is very extremely similar to the previous question. Now the thing is, guys, even the ring is mobile, so even that can move. And in fact, by Newton's third law, we can say that if the bands pull the smaller mass with a force of 3kr towards the center of the ring, then the force on the ring will be 3kr in the upward direction. Okay, so this is by Newton's third law. So the force on the ring is also going to be 3kr in magnitude. Now guys, we need to keep in mind r is the distance between the mass and the center of the ring. Okay, it's basically OP vector. So just keep that in mind. Basically, we have a 2m mass over here and an m mass over here. And in between, we can consider a spring whose spring constant is 3k. So this is like a two body problem, right? Just like where, okay, so basically where we use the reduced mass result and all, right? So here, now for this two body problem, for its oscillatory motion, if you want to figure out the time period, you can use the formula 2 pi square root of mu by k. Okay, but I'm ignoring this formula. We'll just use differential equation to find the time period and all. Okay, but yeah, I just want to show this. So again, let's assume the distance between these two masses is r. So the force on the m mass will be 3kr, and similarly the force on the 2m mass is also 3kr. Okay guys, so now we have to choose an origin about which we can analyze both of these masses, and the best point here will definitely be the center of mass. And the reason for that is, firstly, the net force on the system is 0, plus 3kr minus 3kr, so the net force on the system is going to be 0. And the velocity of the center of mass initially is also 0. So if the initial velocity of the center of mass is 0 and there is no force acting on it, this just means the acceleration of the center of mass is 0. So acceleration is 0, velocity is 0, which means the point will not move. So basically center of mass is going to be a fixed point in this case. So this is a perfect point for analyzing both the motion of both the masses, right? Because it's always fixed at this particular point. And where is this point? So initially it was given that the distance between both the masses is r0, right? Now the ratio of masses is 2:1, which means the distances are going to be in the ratio of 1:2. So if I have to divide r0 in the ratio of 1:2, this distance is going to be r0 by 3, and this distance is going to be 2r0 by 3. So this is how the distances are. Okay, so now let's write down the differential equation, and then we'll try to figure out how the motion of the particles are. So taking center of mass as the origin, okay guys, so now I'm making a claim, and the claim is that both the particles are going to perform simple harmonic motion with the center of mass as the equilibrium position. So this is clearly the extreme position where the particles are left, but I'm claiming that the center of mass is the point which is the equilibrium position. So basically equilibrium position is the point where the net force on either of the mass is 0, right? As I said earlier, the center of mass, the coordinate of the center of mass will remain fixed. Okay, so now I have a question for you guys. So the 2m mass is going to move towards the right. So at some point of time, the ring will reach the center of mass, right? So at this particular instant, where is the small m mass? And the answer to that question is that the small m mass will also be at the center of mass. And the reason for that is, as if the small m mass is over here, if the 2m mass is at the center of mass, then that means the center of mass is somewhere else, right? So if we want the center of mass to be over here, then both 2m and m has to be at that particular location. And if you observe at this particular location, the net force on by the elastic bands on the smaller mass and the 2m mass are both 0. Why? Because the mass m is in the plane of the ring, right? So we can say r equals 0 in this case. In the 3kr formula, right? This is basically the case where m is at the center, or basically r equals 0. So the net force on the mass m is going to be 0. So this is the reason why the center of mass is the equilibrium position. So now once we know that, now the question is simple. So let's talk about the smaller mass first. So Cm is the equilibrium position. Its initial location, which is 2r0 by 3, is the amplitude of SHM, and this is going to be the extreme position, right? So let's move this aside. So now let's write down the differential equation for the smaller mass. Okay, so let's say this is the center of mass. Okay guys, so now let's say at some general instant, the distance between both the masses is small r, which basically means the distance from the center of mass to the smaller mass is going to be 2r by 3. So the distance from the Cm to the smaller mass is actually 2r by 3. Alright, so now we took the distance as r, so the force will be 3kr. So the force on this smaller mass is going to be 3k times r. Okay, so now we'll write the equation of SHM for the smaller mass. So we can say, so now once again in the direction of displacement, I'm assuming the direction of acceleration. So I can say m times 2r by 3 double dot, right? Because that's a position vector, right? Equals net force towards the right, which is actually minus 3kr. So from here we get, from here r double dot turns out to be minus 9k by 2m times r. So this is once again the equation of SHM with omega square equals 9k by 2m. Now if you observe something, for the 2m mass also the equation is exactly the same. There the position vector will be r by 3 instead of 2r by 3. Right, so there won't be any r by 3, but the mass is 2m. So that 2 comes outside here. But other than that, the equation is the same, which means the differential equation is the same for the 2m mass as well. So therefore, both of them will have the same time period. Okay, so the m mass is performing an SHM with amplitude 2r0 by 3. So when the m mass will reach a distance of 2r0 by 3 on the other side, the 2m mass will reach its extreme position on the other side. So basically they both have the same time period of SHM. Okay. Now the first question they asked is the time period of SHM. So that is just going to be 2 pi square root of 2m by 9k, which is just 2 pi by omega. Okay guys, so now let's analyze the motion a little bit. So the ring is going to perform SHM. So I'm going to draw the ring as a thin line, okay, so that we can visualize it more. It is going to perform an SHM of magnitude r0 by 3, something like this, okay. And the small m mass is going to perform an SHM of 2r0 by 3 above the center of mass. So this is going to look something like this. And their time periods of oscillations are the same. When the ring goes to r0 by 3 on the other side, the small m mass goes to 2r0 by 3 on the left side. Okay, this we can also see by the fact that Cm will remain here, right? So if this comes to r0 by 3 on the right, then this has to be 2r0 by 3. Otherwise the Cm won't be at this particular location. So yeah, this is a little bit about how the motion is going to be. The initial location of the ring was over here, right? So we can clearly see that the mass m during its motion will go towards the left of the table. In the motion of mass m, it will cross the ring center. Which means if we keep a table over here, it will collide with the table. Okay, and that's why we have to assume that these two masses are placed in a gravity-free environment. Okay, so now again let's go back to the original configuration. So now we have to write down the position vector of both of these. So once again, first let's write it for the smaller mass. Now the smaller mass has an amplitude of 2r0 by 3 about the center of mass, right? So the x coordinate of the smaller mass. So first I'm writing everything with respect to the center of mass. Now the SHM is starting from the extreme position, guys. So whenever we start from the extreme position, the displacement function is going to be a cosine one, right? So it will be equal to the amplitude, which is 2r0 by 3 times cos of omega t. And omega is basically square root of this term, right? So this is the x coordinate of the smaller mass with respect to the center of mass. Now the x coordinate of the 2m mass with respect to the center of mass is going to be its amplitude r0 by 3. But here if you observe, the particle is at the left extreme. So this is going to be a minus cos of omega t. Okay, because initially at time t equal to 0, the coordinate is minus r0 by 3, right? So this function is going to be minus r0 by 3 cos omega t. If the particles were at the equilibrium position, then it will be a sine function. If they are at the extreme positions, then it will be a cosine function. So this will be a minus, so this will be minus r0 by 3. Okay, so now if you check the answers in the book, guys, it will match with these two answers, okay? But this is not what they asked in the question. What they asked in this second question is we have to take the initial location of the center of the ring as the origin. And that particular point is this point over here. Okay, so we have to write the positions with respect to this point, not the center of mass. So these are not going to be the answer to the problem. Again, it is pretty easy because the center of mass's coordinate with respect to O is at a distance of r0 by 3 I cap. So we can say with respect to the point O, the coordinate of the center of mass is equal to r0 by 3. So basically all we have to do is add this to both of these terms and we'll get the position with respect to the point O. So the position of the mass m with respect to the point O is equal to the coordinate of the mass m with respect to the center of mass plus the coordinate of the center of mass with respect to O, 9k by 2m times t. So this is the x coordinate of the mass small m, and the x coordinate of 2m with respect to O is going to be r0 by 3 minus r0 by 3, and this will be the coordinate of the 2m mass with respect to the point O. So yeah, these would be the answers to these questions, guys. If you have any doubts, you can definitely comment down below. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.